Okay, hello, welcome to the CS353 review for Exam 1. I'm going to be going over the slides that I just released online. So, in terms of what you need to study for the exam, I kind of broke this down into chapter and important topics per chapter. The first one being the data representation chapter, which is Commer, chapter 3. There's also some stuff that we studied beyond the Commer book that you should be responsible for, things like Booth's algorithm, certain other types of binary arithmetic, namely adding and multiplication, floating point representation is important to know as well. Actually, error detection and correction, there's supposed to be a cross out through this. We never got to this. I think we got to it and then immediately had an emergency, so I'm not going to be testing you on error detection and correction. So for that part of the slides, feel free to admit it. And then the next thing we went on to is, this is when Dr. Bresnay was there, went on to Chapter 4, which is processors and the computational engines. So namely the von Neumann diagram, different types of processors, hierarchical structure, conventional processor structure, ALU, store programs, and how that works with the fetch-execute cycle. You should be able to trace out programs and how they're loaded from stored programs in memory into the registers and how they're executed. And also you should be able to talk about the clock rate and the instruction rate and the differences between those. You should be able to talk about opcodes, operands, and the results, specifically what the instruction format is for those, what the registers look like and what they're used for, and pipelines and instruction stalls. You should also be able to cover forwarding concepts, especially in terms of the instruction stalls and the pipeline with forwarding of instructions. You should be able to cover, or you should be able to talk about the program counter, the fetch and execute cycle, especially as I was mentioning before in terms of being able to trace out the how the stored program is loaded into memory and executes depending on what the instructions are. The next chapter that you need to be able to cover is Chapter 5. And Chapter 5 is processor types and Chapter 6, operands and addressing and instruction representation. So there's 3 types of address designs for operands. 1 operand, 2 operand, and 3 operand instructions. You should also be able to talk about the sources and the idea of immediate values, that is a number being loaded right away in and not needed to go to the registers to get that number. You should be able to talk about the von Neumann bottleneck and operand encoding. So in terms of binary arithmetic, you'll be responsible for converting to binary. Here's the number 147 converting to binary. I just wanted to remind everyone how this is done. If we divide 2 into 147, we see that it goes 73 times with the remainder of 1, and we write down the 1. And we see that 2 divides into 73 36 times with the remainder of 1, we write the 1 down again. 2 divides into 36 18 times with the remainder of 0, we write the 0 down. 2 divides into 18 9 times with the remainder of 0, we write the 0 down. 2 divides into 9 4 times with the remainder of 1, we write the 1 down. 2 divides into 4 2 times with the remainder of 0, we write the 0 down. 2 divides into 2 1 time with the remainder of 0, we write the 0 down. And finally, 2 divides into 1 0 times with the remainder of 1. We let and read from the bottom up, and we get our answer of 1001 0011, and that is the number 147 in binary. If we want to convert to hex, this would be another good one for you guys to know about. Converting to hex, you have to break up into groups of 4 for hexadecimal conversion. For example, 1110, 1001, 1101 can break up into 3 groups of 4, being 1110, which is C, 1001, which is 9, and 1101, which is D. Sign magnitude addition is easy. All you need to do is, if you're adding the numbers 0, 1, 0, 0, 0, 1, 1, 1, 1 to 0, 0, 1, 0, 0, 0, 1, 1, then you just add right here, and you take care of any carries up here. So we have 1 and 1. The total of that equals 1, 0. 1, 1, and 1. The total of that, of course, is 1, 1. We carry that, and we get 1, 0 again. We get 1, 0 again. We get 1, and that carries to down here, and then 1 and 1 finally. For 2's complement, we want to remember that we're basically taking, we need to take, say, the negative numbers and flip these and add 1 to them. So if we're going to add 9 with 8 bits, that is 0, 0, 0, 0, 1, 0, 0, 1. Negative 23 is actually 3 ones and then 0, 1, 0, 0, 1, because the actual number 23 is 1, 0, 1, 1, 1, but we flip these and we get 1, 1, 1, 0, 1, 0, 0, 0, and we add 1, and then we get this. Therefore, when we're adding these, we have to add it as such, 9 to negative 23, and then we get the 2's complement value of negative 14. So the Boost algorithm basically says that if the current multiplier bit is 1 and the preceding bit was 0, we're at the beginning of the string of 1, so subtract the multiplier can from the product. If the current multiplier is 0 and the preceding bit was 1, we're at the end of a string of 1, so add the multiplicand to the product. If we have a 0, 0 pair or 1, 1 pair, we don't have an arithmetic operation, we do a shift. We also assume a mythical 0 as the previous bit for the first time we pick bits. So that means when we're multiplying the number 1, 1, 1, 0, 1 with 0, 1, 0, 1, the first thing we do is we take the 1 and we say 1, 0 because the previous bit was 0, and we subtract 1, 1, 0, 1, which is essentially adding 0, 0, 0, 0, 0, 0, 0, 1, 1, because we're taking the negative value of this, which ends up being flipping it and adding 1 to it, and we get 1, 1, and then a bunch of leading zeros. The next time in, we take the 0, and we see that before that we had a 1, so we add 1, 1, 1, all of these 1, 0, 1, because these are the leading ones, to make this into 2's complement to the product. That's called sign extension. Next, we take the 1 and multiply, and so we see that the one before this was 0, so we do a subtraction. And we're subtracting 1, 1, 0, 1, so again we're adding 1, 1 with a bunch of leading zeros. And we see that the next one is 0, 1, so we add the multiplicand again to the product, and we add all these up. So we add up this one, this one, this one, and this one. We add all those up, and we use the 8 rightmost bits. Therefore, we have negative 3 times 5 equals negative 15, because we're using this bit 1, 2, 3, 4, 5, 6, 7, and 8. So that ends up being negative 15. Now, remembering converting to floating point is important, especially if we're taking the number 0.03125. We have to basically first convert that into binary, which to do that we take the 0.3125, multiply it by 2, we get 6.250. We remember that we got a 0 here, because that's going to be important later. We multiply it again, we get 0.12500. We get a 0 here, that's important later. We multiply it again, we get a 0 here, 0.2500. We multiply it again, we get a 0.5. Finally, we multiply that by 2, and we get a 1 finally. And then we take this from top down, which is 4 leading zeros and a 1. So first we cut off those leading zeros and we figure out what to raise it to. And in this case, we're going to raise it to the negative 4th power, because 0.0001 times 2 to the 0 is 0.001 times 2 to the negative 1st, which is 0.001 times 2 to the negative 2nd, and so on until we get to the negative 4th. And then we apply the bias, which is 15 minus 4, which is 11. Therefore, our answer is 11. And then with our our 3, 1, 2, 5 here, so the exponent equals 0, 1, 0, 1, 1. The significand is 1 with 7 trailing zeros. I attached a bunch of other slides to this deck of important things to consider in terms of the review. It's important to note what the von Neumann, the four main components of the von Neumann architecture, the processor and memory, all of which are can communicate between the input and output facilities, and then the computer being the entire grouping of the processor, memory, and input and output facilities. Here's the illustration of a processor hierarchy on a CPU. Now, normally that exists by the notion of an ALU, which is our arithmetic logic unit, and our controller and our local storage, as well as our external interface. Here's steps in a microcontroller performs, for example, for an automatic door. This is a hypothetical machines. Hopefully Dr. Bresnik covered this with you. This is a hypothetical machines instruction format and integer format. And then this is how that actually works. If you take a look at the PowerPoint slides that I've posted and actually download them, there's a lengthy description of this slide in particular inside of the PPT. So if you don't know how this is working, you can download that PowerPoint and get it. The opcodes are listed here. Load AC from memory, store AC to memory, add AC to memory, which is the number. So for example, store AC to memory is number 2, add to AC from memory is number 5. And the way this works is our memory, loads into our instruction register. Our instruction register is translated, and this says take 3, which is position 940, so it's saying do 1, which is load AC from memory. AC is here, and we're adding this address position 940 from memory, so we put 3 there. On step 3, say update the program counter. So we're doing 5941, which we look again at 5, that is add to AC from memory. So we're adding to AC right here, which is our 941. So we're adding 3, which is in AC. The number that's being referenced here in 941, which is 2. So that's 3 plus 2 equals 5. That goes into AC. The next step is 2941, which is store AC to memory. So we know that we have to store this into 941. And so we take the AC, and again, we store this in 941. And that is how a program executes. Hopefully you understand that. And all of that is kind of summarized in this diagram here. That involved a number of cycles, the fetch cycle, the decode cycle, execute cycle, and here's a typical instruction format as covered by Kommer. This was the idea of storing in register banks. That's similar to what we just did with that full trace out, where we were in our register banks here in our CPU register. And then we have to assign registers to banks. this slide indicates that even trivial problems or trivial programs can cause problems. For example, x plus y is loaded into the R bank, but then z minus x is loaded into the S bank, and into T we get y plus z. So what that means is the value of z minus x, for example, is dependent on x being available, and the value for y plus z is dependent on z being available. Let's just go over that again. In this case, x and y are placed in registers from opposite banks. So if we assume x is in register bank A, y is then in register bank B. But for the subtraction, z must be in a different bank than x. So that must be in register bank B. But for the third assignment, y and z must both be in different banks. But unfortunately, in the first two assignments, y and z are located in the same bank, and therefore y and z cannot be operated upon. Okay, the rest of these are pretty self-explanatory. This is the list of stages in a pipeline. You can see that each stage has a separate instruction at a separate stage. Pipeline stalls can happen when they're using the same registers. For example, this is showing that in an instruction stall if we're waiting for the operand C to become available. And this shows what that looks like in terms of a pipeline stall. You can eliminate these stalls by rearranging. You can also forward, which allows ALU to reference into the next instruction. Here's a list of standard MIPS instructions. These are probably useful to just get used to, especially in terms of add immediate, which does in constant. You say add immediate like 7, for example, and that immediately adds 7 to whatever is in the register. Here are some zero address instructions like push and pop and add. One address instructions like the add immediate 7, load x, store x. Add 7 to x is a 2 address instruction. Add x and y and place it in z is a 3 address instruction. These two slides talk about how the opcodes look and the operands look in terms of each other, so that's something good to take a look at. And that's about it for the purpose of the review. Alright, that was a 20-minute long quick review of everything. If you have additional questions, feel free to email me. Thanks. Oh, by the way, the test, you should keep in mind the test is going to be composed of about 10 to 20 multiple choice questions and 5 to 10 short answer questions.